video, we're going to start looking at voltaic cells, also called galvanic cells or even electrochemical cells. So you should have already looked at redox reactions where you have something oxidized which loses electrons, something reduced that gains electrons. A redox reaction is really just a transfer of electrons. And if you think about it, we can actually use a redox reaction to create electricity because moving electrons is electric current. Anytime you have moving electrons, you have electricity. And redox is a transfer of electrons. You have something moving from what's oxidized to what's gained. So if you look at this example, if you were in my class, then we might have done this example in class. Here's a redox reaction. We could break it down into two separate half reactions. You have a reduction half where you see electrons are being gained. In this case, 5 electrons are gained. You have an oxidation half where you have electrons being lost. And so you do have this transfer of electrons from whatever's oxidized, in this case the Fe2 plus is oxidized, it's going up in oxidation number, to what's reduced, in this case the MnO4 is reduced because the Mn's going down in oxidation number from +7 to +2. So if this were to happen in the same beaker, let's say, in the same container, the electrons would just immediately transfer from what's oxidized to what's reduced without really doing any kind of meaningful work. But how can we actually harness this energy? How can we create this flow of electrons that can be used as electricity and do useful work, like as a battery? We can actually separate the reactants so that the electron transfer is forced to happen through a wire, so that you have these electrons flowing through a wire. You have this electric current, which you can then use to power something that wouldn't ordinarily happen, like what you do with a battery. So what we're going to do is we're going to take each of these half reactions and have it happen in a separate container. So for a voltaic cell or a galvanic cell or electrochemical cell, you're going to need two containers, one for each half reaction. So if we take these two half reactions, notice my reactants, you have this permanganate, you've got an acidic solution here. Notice my reactants here, I've got Fe2+. If I take them and separate them into two different containers, then I can make these electrons flow through the wire from the oxidized half reaction down to the reduced half reaction. But what happens is, even if the reaction starts, it stops immediately because you have these electrons start building up. And what are the charge of electrons? Electrons are negative. And what do we know about like charges? They start to repel each other, so that's going to stop any more electrons from flowing this way. Essentially, too much negative charge has built up in this container, and we've got this repulsion. So how can we stop that from happening so that this reaction can keep happening? Because I've still got other reactants left over in my containers that we can use. Basically, we've got to start reducing this negative charge. Okay, well, how can we do that? What are some other things that have charge? Not just electrons. What are some other things that have charges that can move? Mobile charges. Oh, wait a minute, ions. We can use ions or salt. Salt is another name for an ionic compound, to kind of help equalize the charge so that this reaction can keep happening. So what else can provide mobile charge? Salt. So what we need, and if you've taken physics, you can almost think of this like completing the circuit. I have negative charge going through the wire in the shape of electrons this way. I want to send negative charge back the other way. I need to bridge these two containers with something that provides mobile charge, like a salt. So we are going to eloquently call this a salt bridge, because it bridges the two containers and it contains a salt. So usually a salt bridge is a U-tube filled with some type of strong electrolyte. Why strong electrolyte? We want that salt to 100% ionize so that these ions can separate. You know, they're not found together as a neutral ionic compound. They're found as these mobile ions with separate charges. And then these ions can flow either way to prevent charge buildup. And we want to make sure that our salt is something that's not actually involved in the reaction, some type of helper ion. So notice that I've got like permanganate here, I've got Fe2+, so I'd want my salt to be something that's not permanganate, that's not iron. So maybe something like sodium chloride, NaCl, even what you normally think of as salt. Again, make sure it's going to be a strong electrolyte, so you might want to know your solubility rules here for the AP exam. We want to know that it's group 1, like Na, K, ammonium, or nitrate are great things to have as our salt because we know that they're soluble. Okay, so example NaCl. So what does this salt bridge do? It actually completes the circuit. So let's follow what's happening. So again, here's my oxidized half cell. Here's my reduction half cell. The electrons are going to go from what's oxidized through the wire to the other electrode into the solution so that that can now gain an electron. And then what's going to happen is, okay, now I've got this negative charge building up here. I'm going to send this positive ion in here into this half cell so that we are now neutralizing the charge. I don't have this charge buildup because don't forget, in every kind of reaction, we want conservation of mass and charge. And then the negative ion is going to go in here because we've just lost an electron. We are having this buildup of maybe positive charge here, right? Fe2+ was turning into Fe3+, if you remember the half reaction. So we're going to send the negative ion here. So you can think of it as, the positive going where you have a buildup of negative, the negative going where you have a buildup of positive. Or you can also think of it as here's the negative flowing this way to complete the circuit. The negative, in this case now ions, should go this way. So notice the electrons go through the wire. Ions, which are not immediately involved in the reaction, go through the salt bridge. Okay, and here it's happening again. There's the negative, follow the negative ion, now goes this way. And so you have this completion of this negative charge, so you don't have a buildup anywhere. So negative ions flow to the side where negative electrons have been lost. Positive ions flow to the side where negative electrons are gained to prevent charge buildup. And Na+, Cl- are not involved in this reaction. They're just these helper ions, or even like spectator ions. If you were writing an anionic, they wouldn't be in there. And they're just helping to complete the circuit and neutralize the charge. Instead of a U-tube salt bridge, you could also have a porous disc where you have strong electrolyte in there, and again, they can go to either side depending where you need the charge to prevent the charge buildup. Okay, the electrons are actually being transferred from these electrodes, which you will see. We'll talk about what these names are from an anode and a cathode, but the electrons are transferred at these electrodes, and then they go through the wire. So electrons are transferred at the interface between the electrodes and the solution, and the salt bridge, or in this case there would need to be a porous disc, would allow ions to flow, not electrons. Okay. So just a few definitions here. A voltaic cell, also called a galvanic cell, is a device where you are actually taking chemical energy and changing it to electrical energy. You're taking this chemical redox reaction, you're harnessing this flow of electrons to create electrical energy, which then can power something else that doesn't normally happen. So these voltaic cells can act as a battery. Sometimes they're also called electrochemical cells, hence electrical and chemical. These are always involving a spontaneous chemical reaction. So it's taking a chemical reaction that is happening by itself without us forcing it to happen. So if it is spontaneous, remember that your delta G, your Gibbs free energy change, is negative. It is thermodynamically favorable. And you are producing a flow of electrons, and this is why these could be used as batteries, which we will see later. Electrolytic cells are also cells that exist. The noun for it is also called electrolysis, and that's where you're taking a non-spontaneous chemical reaction, something that has a delta G that's positive, and you're taking this non-spontaneous reaction and you're forcing it to happen by providing electrical energy. So this is going to require a flow of electrons, some type of plugging it into an electrical outlet or using a battery, and this is where you would take electrical energy and change it into chemical energy, and we will see that in another video. Okay. This requires a redox reaction. You need these electrons transferring in order to make this flow of electrons. The two surfaces I was just talking about are called electrodes, those two pieces of metal that you saw soaked in the solution. And this is where the actual redox reactions occur. The anode is where oxidation occurs. The cathode is where reduction occurs. So know those terms. A shortcut or a little mnemonic device is anox, anode is oxidation, red cat, reduction is at the cathode. Okay? These pieces of metal may or may not be the things actually oxidized or reduced. It might just literally be the surface it takes place on. So that's why I'm not saying anode is oxidized, the cathode is reduced. It's where the oxidation occurs. Cathode is where the reduction occurs. It's a piece of something that conducts electricity, typically of metal, and where these actual half reactions are happening. So these must be some type of surface that conducts electricity. Remember, metals have metallic bonding between your atoms, and that's why they can conduct electricity, because the electrons are mobile. Electrons always flow through the wire from anode, because that's the site of oxidation, you're losing the electrons, to cathode, because that's the site of reduction, where you're gaining electrons. Always, 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 anode to cathode through the wire. And that's alphabetical order, A to C, so that's kind of easier to remember. Okay. So, a lot of the times you might be asked, given a diagram, or even asked to draw one. So let's practice how we can draw an a voltaic cell based on a redox reaction. So here's an example. Here's a redox reaction, and let's say I want to build a voltaic cell off of this reaction. So the first thing is, let's figure out what's oxidized and reduced, and let's take a moment and write the half reactions for the oxidation, the half reaction for the reduction. So if you want to pause the video, take a moment, try that. We'll go over it right now. So Zn is going from 0 to 2 plus. Okay, so the Zn is what's oxidized. Cu is going from 2 plus to 0, the oxidation number. So the Cu2 plus is the thing that is reduced. If we're writing our half reactions, okay, we notice that the Zn is changing into Zn2 plus. So let's write that down, and then we just have to add in our electrons. 0 to 2 plus, we need to make sure our charge is, conserved. So if there's 0 on this side, we need to bring this side down to 0, so we need 2 electrons. And if this is oxidation, it makes sense that electrons are on the right. There should be 2 electrons lost. 2 plus, 2 minus, now cancel out to 0. Let's take a look at this half reaction to figure out what's going on in our half cell that is housing the oxidation half reaction. So notice that should be Zn solid. We need that to react. So that's what we're going to make our electrode out of. We're going to make it out of the Zn solid. And over time, okay, the Zn is going to be changing to Zn2 plus. So what's going to be happening to this electrode over time? It's going to start losing mass because it's changing into Zn2 plus, which is in the solution. So oxidation is occurring. Remember that electrode is called anode, the site of the oxidation. In this case, it's going to lose mass because I'm going from the solid, which is being used up, to Zn2 plus, which is made in solution. So over time, that anode is going to get skinnier and skinnier over time until it might get completely used up. Okay, how do I know it loses mass? I'm looking at the half reaction. So anode does not always lose mass. You have to look at the half reaction and see what's going on. Okay, and if I write my reduction half reaction going from Cu2 plus to Cu, if you're having trouble writing half reactions, go to my video about writing half reactions. I would need 2 electrons on the left so that the charge is conserved, and it makes sense. Reduction, I should be gaining electrons. In this case, I need 2 of them. And this would be happening at the cathode. Reduction is happening at the cathode, red cat. And if I look at what's happening over time, Cu2 plus would be coming out of solution and turning into Cu solid at the cathode. So over time, this cathode is going to start gaining mass because you are making a solid at that site. Now, even though Cu solid is not really needed for the reaction, notice it's not a reactant, it's being made over time. Typically, if you have a certain metal in your reaction, you will make your electrode out of that metal to ensure that no other metals are reacting, that only copper is involved here. You could technically make it out of something like platinum, which is a very unreactive metal, but it makes more sense to not involve another metal if you don't have to. Okay, so let's talk about you're going to end up having this voltaic cell, which looks something like this, two separate containers for each half reaction, a salt bridge, electrons going through the wire. Maybe you have a switch, maybe you have a voltmeter, which aren't really needed, but you might see that along your wire. And let's just talk about how you can kind of draw this yourself. Okay, so when you're drawing a voltaic cell, you need to make sure in your drawing you have two containers. One that holds the anode and the solution that is needed for the oxidation half reaction, and the other that's holding the cathode metal as well as whatever's needed for the cathode half reaction. Each of these cells are called half cells because together they make the electrochemical cell. Sometimes these anodes and cathodes are reactants, and sometimes they're just surfaces for something to take place on. So if you remember kind of our first reaction, even if I just kind of scroll back to it for a second, here, if you kind of remember our first reactions, there were actually no metals involved in either of these half reactions. I could have made these metals something like platinum, which is a very unreactive metal and doesn't tend to either oxidize or reduce. But, you know, if there is a metal involved, typically we make it made out of that metal. Okay, so platinum, even graphite. Each container has to hold a solution that is needed for the reactant. So look at your half reactions. You know, typically if zinc is, let's say, your anode, you're going to end up having zinc ions in that solution that houses the metal. But look at your half reactions to see what is actually needed in those containers. Don't forget you need wire connecting anode to cathode because electrons go through the wire always from anode to cathode. They don't go through the salt bridge, they go through the wire. And don't forget you'll also need a salt bridge to prevent charge buildup, to allow the flow of ions in the form of some type of strong electrolyte that's not actually involved in the reaction. Okay. So let's do an example. Let's look at this example here. We're going to do all of these things. Figure out what's oxidized, reduced, anode, cathode. Draw a voltaic cell. Write the half reactions. Tell me which electrodes are gaining, losing mass. Show me the the direction of ion flow. All right. So let's do this first one. So let's figure out what's oxidized and reduced. And again, you might want to pause the video first, try all these things, and we'll do it together. So Cu is going from 0 to +1, so it's oxidized. Ag plus going from +1 to 0. So Ag plus is actually the thing that's reduced. Let's start drawing this voltaic cell. So I know I need two containers. Let's put one metal, let's put Cu in one container, and let's put Ag in another container. So Cu is Cu solid is the thing oxidized. So this electrode is going to be the anode. Ag we'll use for our cathode because that is the site of reduction. And notice that even though it's Ag plus that is reduced, I don't actually need the solid to start with. I'm going to make this electrode made out of silver so that I know no other metals that are needed, that are not in the reaction are involved, and that would probably be best. Again, if you wanted to use graphite because, the silver could latch on to there and turn into silver solid on top of it, yeah, you can make the argument that that would work, or platinum or something. But typically, if there's metal ions and metals involved, use the metal that goes along with that. Okay, so then we need solution in here. So in here, you don't necessarily need the Cu plus to start with. As you see, it's being made over time, but over time you will get Cu built up. In here, I actually need the Ag plus in there to start with, or else no reaction is going to happen. It is actually the thing that gets reduced. It is actually the thing that is a reactant. Okay. How do you get Ag plus in there? Maybe you add AgNO3 because NO3 is, always soluble. So you want to add some type of strong electrolyte that is a source of Ag plus. Okay, then you also need a wire connecting the anode to cathode, and electrons will go through that wire. Maybe there's a switch. It would have to be closed in order to work. Maybe there's a voltmeter on it where you can actually measure the voltage, but neither of those things are actually needed. and electrons will go through the wire from anode to cathode as this redox reaction happens. If this is the oxidation half reaction, as we saw, copper is oxidized, and oxidation happens at the anode. If we're writing the half reaction, look that the Cu is going to Cu plus, and it makes sense. Copper has a 0 oxidation number. Cu plus has +1, so that is being oxidized. It's going down in oxidation number. Electrons would be on the right, and I would need one of them to equalize the charge. It is actually Cu solid that is oxidized. So notice that Cu solid is both the anode and it is the thing that is oxidized. Okay. Over time, Cu solid would be coming off of this and turning into Cu plus as it loses an electron and the electron goes through the wire. And over time, this would start to lose mass and get skinnier and skinnier as the reaction happens. Why does that happen? I'm literally looking at the half reaction to see that. Okay. On this side, this is the cathode, so this is reduction. If it's reduction, it should be going down in oxidation number, which makes sense. It's going from Ag plus 1 to Ag 0, and I would need one electron on the left to balance the charge. And in this case, you'll notice that Ag plus is the ion, is the thing that is reduced. Ag solid is the cathode. So they're two different things. Ag plus is reduced. Ag solid is the cathode. So make a notice of that. Over time, Ag plus is turning into the solid at this cathode as the electron gets accepted. And over time, this would get coated with Ag solid and it would gain mass over time. How do I know that? I'm literally looking at the half reaction. So again, notice it's Ag plus that reacts, and this original cathode could be graphite, could be platinum, because it's not actually silver, but let's ensure that nothing, if we can, let's ensure there's nothing else involved, and let's make it silver. And notice that Cu plus doesn't necessarily have to be there, but it would be building up over time. Don't forget your salt bridge so that this can continue happening. Maybe let's put something that's not Cu, something that's not Ag, something not involved in the reaction, something like NaCl, something that fully 100% ionizes, so make sure you choose a strong electrolyte. Typically group 1 ammonium nitrate are your solubility rules to memorize. And if the electrons are going this way, negative charge, to complete the circuit, the negative charge should go to the left through the salt bridge into this half cell, the oxidation half cell, which makes sense because over time I'm building up positive charge. That will help to neutralize that. The Na plus would go this way to help the charge build up of the negative charge build up to cancel that out.